Test 1 2. All right. My name's EJ Daigle, again, Dean of Robotics and Manufacturing here at Dunwoody College Technology. I'm going to give you a little demonstration on RS500's sequencer instructions. All right. First and foremost, sequencers, specifically sequencing, can be really handy when outputs. I don't know why I've got should be a little space here. When outputs need to follow a designated known sequence. Sequencing instructions are advanced instructions that use the power of storing bits or numbers in data files. So as an example, let's say that you had some outputs. I've seen lots of different examples of this. We're at a cookie factory, and we want to lay some stripes down on a cookie, and then we want to lay two the other way. Or in some cases where we have different batches and we want to mix 3 ingredients, and maybe at this point we want to put in ingredients 1 and 3, and then we want to put in ingredients 2, and then we want to mix them up or something like that, or add water or different things. Rather than controlling each one of those outputs individually, and having timers and counters and all those things that you might need, if I know my sequence, like if I had 1 2 3 here, if I know my sequence is, well, I need 2 for 5 seconds, then I need 1 and 3, and then I need 1 2 and 3, and then I need 1, and then I need 2 for a little bit of time. If that was my sequence that I needed, you totally could do that. And if there was a time step between each one of these, 5 seconds or 5 minutes or whatever it was, you completely could do that. Mind you, you would have a lot of rungs of code, and your code would be written at kind of a lower level, and it wouldn't take advantage of these great data files that Alan Bradley's put in there for us. Another great example of a sequencing instruction would be something like a traffic signal light, right? We have green, yellow, and red. We have one on the north-south intersection, then we also have one over here on the east-west intersection, right? Green, yellow, and red. And I know that when this one is green, this one should be red, right? And when this one then turns yellow and then red for a certain amount of time, then this one turns green. Well, that's a simple sequence. You don't have to have a long slew of daisy-chain timers and counters and things, each individually latching and unlatching bits. That doesn't need to happen. We can do it with a sequencing instruction, and take a program that maybe is 20 or 30 lines of code and condense it down to even as little as 1 line of code. So this will be our first real advanced instruction that we're going to use within the RS500 software. I'm not going to get into detail. This, you can find this definition in the instruction help files in RS500, but the SQO, this is going to be one of our primary commands that we'll use with sequencers. We typically place it as a block instruction. It goes on the right side of the rung as an output. When the rung transfers from false to true, the instruction is incremented to the next step in the sequence. So you can have several steps. I can go from step 1 to 2 to 3 to 4 and so on and so forth. Data from the sequencer file is then transferred through a mask. So the mask allows me a secondary control. And if anybody's wondering what a mask is, well, if my sequencer is 1 0 1 0 and my mask is all ones, so this is my sequencer data and this is my mask, all right, then it's just a logical AND. I AND those two together. Well, 0 and 1 ANDs out to a 0. The only way I get a 1 out of an AND gate is 2 ones, right? So this would AND out to a 1, this would AND out to a 0, and this would AND out to a 1. So you can see I push my data all the way through. But in the case if my sequencer was 1 1 0 1 and my AND was 0 0 0 1, then in that case, the only one that would AND out is a 1 here. Everything else would be a 0. So the mask just gives us some additional controls that we can build into the sequence. You'll see that here in a few minutes as I step into the demonstration here. All right, so the first thing that we look at is the file address of the sequencer. And you can use an integer file for an address. You can use a binary file. It's very common to use a binary file as the address for your sequencer, but that's where my data is going to be stored essentially. And then I have a mask, and the mask is a hexadecimal code. If you want the mask to do nothing, then I would address the mask as FFFF. H, standing for hexadecimal. And what that means is each one of these F is a hexadecimal corresponding to 4 ones. And so there's 4 ones, 4 ones, 4 ones, 4 ones. So it doesn't matter what sequence of 16 bits I'm going to mask with this, or I'm going to AND with this, they're all going to pass through. It's kind of like when we do some of the stuff with the subnet mask with IP addresses and things. It's a very similar concept in that I logically AND it to see if it's allowed to be an output or not. So if I was only going to use the first 4 bits, let's say, then I might do 000F, as my mask. And so that would mean that all of these would be zeros, boom, 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 dot, 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 until I got to the last 4 bits. So if I ever ended up with a 1 over here, it would AND out to a 0. But anything, if I was only using the 4 bits, 1 0 1 1, those would AND out to 1 0 1 1. It's just that next level of control that allows you to control what is allowed to be used with your sequencer. The destination is the address of the output word or file that the sequencer output is going to move data from its sequencer file into. In our case, we're going to use an output file, an output word, so we can actually watch these things turn on lights or something like that. And then the control. If you look at what the control is, the control parameter is a control structure to do the following: store the status byte of the instruction, length of the sequencer file, and the instantaneous position in the file. Control address cannot be used for any other purpose. So this will be the first time that you'll see the control file data files used. I tell people, we don't get real deep into what the control is, what's happening with the control. Think of the control kind of like the traffic cop. He's actually, moving the things around, storing them instantaneously, and making sure everything works correctly. All right, so the binary file. So we've used binary files in the past. I'm going to actually, probably when I do my demo, I'm probably not going to use B3. The reason why is that we know that a lot of times we use B3 for other things, right? So we might want to use B3 0/0 for a system run bit, or we want to use it for a system stop bit or something like that. So I tend to make sure that my B3 files are reserved for other stuff. But in this case, I showed you a B3 binary file set up for a sequencer. So I can actually drill into the B3 file, and under properties, you can actually select how many individual words within B3 you want to use. So in this case, I'm using word 0, word 1, word 2, word 3. And then you can see what I did was these first 4 bits, B3 0 is going to be 0, 0, 0. B3 1 is going to be 0, 0, 1. B3 2 is going to be 0, 0, 1, 0. And B3 3 is going to be 0, 1, 0, 0. So if my only goal is to light up, let's say, 3 lamps in sequence, I might move these binary files from the B3 files, let's say, into my output, my O:2.0. So you can see my file is stored in B30. You can see my mask is just that first F. Oops, sorry about that. And the H means it's hexadecimal is all that actually means. And then my destination is the O:2.0. You'll notice the dot there. It's O:2.0. That means I'm addressing it at the word level. And as I take what's in the file here, I'm going to move it out to the output addresses. So in this case, the first step in the sequence, or step 1, I'm going to move all zeros to my output address 20. And so 2.0, I'm only going to use the first 4 bits. So I'd have O:2/2. I guess I need 2, 3 here, don't I? O:2/2. O:2/1, and then O:2/0. And so I have those 4 bits that I can turn on and off, right? And so in the first step of the sequence, you'll notice all 4 of those bits are off. So off, 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 and off. That corresponds to sequence step 1. And then when I get to sequence step 2, what I'm going to do is I'm going to transition. Let me move this guy up and out of the way here. So I'm going to transition to position 1, and in position, I should be careful here. This would be position 0. Sorry about that. This is position 0. This would be position 1. This would be position 0. And now I'm going to transition to position 1. And in position 1, I'm actually looking at this character here, and I see now I have 0, 0, 0, 1. So now that I'm going to transmit that out to the output file, and now that first output is on. And when I get to step 2 of the sequencer, similar things arise, right? I get 0, 0, 1, 0. So now step 2 is going to say 0, 0, 1, 0. And then I get to step 3 of the sequencer. I get 0, 1. So step 3 is going to be 0, 1, 0, 0. And what you can see is with using just one box instruction that we see here, right, this sequencer output file, and setting up my binary data file right here in advance, I can legitimately make these outputs sequence from one to the other, to the other, to the other, and back using just one output instruction. So that's a pretty powerful tool when you think about what this thing is actually capable of doing. If you were doing this before, someone might say, well, I'll flip a switch, and every time when it counts to 1, I'll do a compare instruction and I'll turn on this bit. When it counts to 2, I'll do another one and I'll turn on this bit, or something like that. Or you might use a timer and say, okay, when the timer's from 0 to 5 seconds, this bit's on, and then another timer when it's from 6 to 10, this bit's on. You can see that I could be incrementing this sequencer with a timer or switch, and it could be the only instruction, and I wouldn't need anything else to make this thing happen. All right, so applying the mask, I've talked a little bit about this. So 0, 0, 0F. So when you look at this again, you can see we've got these 4 bits are really the only ones we're using. And one of the ways I know that, well, first of all, I said I'm only concerned about a length 4. I also only set up four pieces of the binary file to be used, right? But the other way that I can control that too is through the mask here. So even if I was setting it up to use all 16 bits of the binary file, I could actually control whether or not there's times where I don't want to use all 16 bits through the mask. So as an example, we saw this, right? We saw that we went from 0, 0, 0, 0, and then we masked it with that F, which is right here. That F there means that 0, 0, 0, 0, 0. These are going to AND out. This is an AND gate. They're going to AND out to 0, 0, 0, 0, 0. Why? That was step 1. The reason being is because if I AND out a 0 with a 1, I get a 0. But then when we got to step 2 of the sequencer, we saw it was 0, 0, 0, 1. But now that's ANDing out with a 1, 1, 1, 1. And again, if I AND that out, I get a 0, 0, 0, 1. So the 1, 1, 1, 1, that's essentially just saying, well, we're going to pass anything through as long as it's those 4 bits. Let's go to step 7, which we didn't do, or some a different step, and let's say that we were gonna send 5 ones through the system, 5 ones, right? So here's 5 ones. Well, you'll notice that next sequence of 4 bits are zeros. So now I'm ANDing out with 0, 0, 0, 0. Oops, not this one. There's my 4 bits. And then 1, 1, 1, 1. So the AND gate now is saying, look, yeah, I'll pass all these through, the 1, 1, 1, 1. But this one here is ANDing out with a 0. So that's going to be a 0. So just think of AND gate. That's what the mask essentially is. It's an AND gate that's determining what bits are being allowed to flow through. And in this case, because we have that F in that first position, this means the sequencer moves through the first 4 bits of the file. We can use data beyond the first 4 bits, but they're going to AND out with zeros. So if they AND out with zeros, you're going to get nothing. Oh, and by the way, you can always change this value, right? So you could change it and say, well, right today I want to use 0, 0, 0, F, H. You also, if I just wanted one more bit, I could go 0, 0, 0, oh, excuse me. Yeah, 0, 0, 0, F, which gave me, all zeros with those 4 ones. I could also do a 0, 0, 0, excuse me, a 0, 0, 1 F, which would give me 1 additional bit in this location to which I could AND with. So you just got to kind of remember your hexadecimal. You might want to review back and look at, oh, how did hex work again? Why did EJ teach us hex in the first week of the class? Well, this is one of the reasons why we need to understand hex. We need to understand that that F corresponds to all of these bits being on, because it's essentially a 15, right, is what it is. 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. Gives me all 4 of those bits on. The destination. So again, we're looking at that same output file that we just talked about. That destination, in our case, is going to be a word. It's going to be the output to word 0. So I could say, output to, /1 or something like that, O:2/1, O:2/0, whatever the case is. In this case, I'm going to use all of the bits within the output file 2. So that's going to determine which of those I'm actually going to use then. So we know that this is slot 2, and a lot of times we say, you know, O:2/1. Well, that means slot 2, and it means bit 1, right? That just corresponds to a single bit. But as soon as I say O:2.0, now I'm saying, hey, slot 2, and as I look at my module here, my slot 2 guy, for my module, you guys will be different. You'll be using DC output module. Mine only has 8 bits because it's a relay output module. What that means is, it means essentially word is what I'm going to address to. That's all of the bits within that slot, okay? So I'm controlling all of the bits, which typically word is going to mean 16 bits, right? So that's a little bit different than what we've done with in the past. So just remember, when you look at this slash, we're talking about a bit address, and we're looking at the dot, we're talking about a word address. Oops, I need to make my D that way, and my bit address is that slash. The control is the memory allocated to move bits around like a traffic cop. So if you're only using one sequencer, we're just going to call it R60, and that just dedicates some memory. You know, I think of it kind of like, I don't know, if you think of old PCs, we might have had, you know, different components in between. So there might have been an arithmetic logic unit, or there might have been some temporary memory. So an input comes in and output goes out, but in between we don't necessarily see what's happening, but there is some sort of memory or some sort of control dedicated to process and store that data. Well, that's really what that control is. The length, this is telling me, well, you know, how many bits are you actually going to use? And then the position's probably one of our more important ones, because we can actually actuate and look at which you know, I don't even know what I want to call it, current bit position. How about current sequence step? You know, it means the same thing, but it makes, I think for the first time learning this, it kind of makes a little more sense. Which step of the sequence am I actually in? That's what I'm more concerned with. All right, so there's a lot of different things that we could do with this, but I'm going to change it up a little bit here. I'm going to discard those annotations for a second, and let me just take a peek here. Oh, one other thing here. Actually, before we jump into the live demo here, I'm going to show you when we do this, creating custom data files. Like I said, I don't want to really mess around with B3. B3, I1, you know, S2, O0, T4, C5, R6, you know, it's the first time we've used the control files, N7, F8. They're all pre-built for you, and I try to leave those alone for using with just my standard PLC programming, you know, kind of at the bit and the integer and at the float level. If I was going to do something with a sequencer, I may want to create my own binary file. This is one of the powerful things about Allen Bradley, is I can create my own binary file, name it whatever I want to name it. What that means is, by doing that, I don't run the risk of using the B30 files for my sequencer, and then mistakenly, I'm so used to using B3:0/0 for my system run bit, mistakenly grabbing it and using it somewhere else, and now I've got the bit being controlled by two different things, or controlling two different things. So I just try to like stay away from that. If I've got a dedicated sequencer operation, I kind of like to put it down here in its own file. Sequencer instructions, you know, we'll use the sequencer output, but you know, I guess I'll read through these real quick. On successive false to true transitions, the SQO instruction moves a step through a program sequencer file, transferring step data through the mask to a destination word. The done bit is set when the last word of the sequencer file is transferred. We're going to actually do that a little different. You'll see that in a second. On the next false to true transition, the instruction resets positions to step 1. Sequencer compare, so starts to make sense here. On a successive false to true transitions, the SQC instruction moves a step through a program sequencer file, comparing the data through a mask to a source word or a file for equality. So it's looking, hey, how do these compare? A sequencer load, on successive false to true transitions, SQL moves a step through a sequencer file, loading a word of source data into the current element of the sequencer file. So this actually would allow me to say, well, what do I want to put into that sequencer file? How do I want to load it up and prepare it for use? Source of this data can be an I/O storage word address, a file address, or a program constant. All right, so those are the big ones. I think the best thing to do, though, is we talk about sequencers, because at this point you're probably looking at this and saying, wow, this is, I'm not sure I understand exactly what we're up to here. So what we'll do is we'll go into the Allen Bradley software here, RS500, and I see I've gone offline here, and that's fine, because you know what, I want to just recreate it anyways. So I'm going to delete this all out, delete the whole thing out. I still got my PowerPoint open. We can go back and reference that. I'll go into RS links, make sure I've got comms again. I unplugged earlier, so that's why I probably lost comms here. I got my configuration successful. Remember, my PLC is a little different than the ones you guys will use in the lab. My I/O configuration only has 4 modules, so I've got my processor, my DC inputs, my 8 relay outputs, and then I've got my analog module. All right, and you're going to see how powerful this is really, really quick. What we're going to do is up here, normally we do a lot inside of our, our bit logic, our users, our timers, or counters. You guys have already been using compare and math and things now, and probably move instructions. So we've used a lot of these different areas, not everything, but now we're going to go into this File Shift Sequencer tab. If you go into that File Shift Sequencer tab, you'll find one of these says SQO. Oh, not that one though. There it is. Sequencer output. I'm going to drag that sequencer output down. Looks just like the one we saw in the PowerPoint there. And then I also have a bit that I'm going to kind of use this to transition it. So I'll use an examine if closed bit of I:2/ let me see which address it is here. I:1/2, excuse me, 1/2. So that's my switch that's going to sequence it. All right, so one of the first things I want to do as I'm working in here is I told you I'm going to delete this one for a second and show you how I did that. I want to stay away from that B3 file, right? So I'm going to have this switch turn this thing on, and we know that we're going to go into a file to get my address here, but rather than using the B3 file, where I like to use that for my system run bits and for other virtual outputs and flags and things like that, what I'm going to do is I'm going to create a new file. So this is something you haven't done before, but it's something that is extremely powerful. So what we'll do is we'll right click on data files right here, and I'm going to go to new. And when I do that, it says, well, what do you want? Well, I want a binary file. I could create more timer files too, so you don't have to have only T4 files or C5 files. You can create timer and counter files or integer files or whatever it is that you want to create. But I do want a binary file. And I like to space it out a little bit, so I'm going to make it as a binary file 50, and I'm going to call it sequencer. So I'm creating it specifically for the purpose of using with my sequencers. And so that'll become my file address where I'm going to get my binary data, B50:0. So I type in B50:0, it adds this little pound sign to the front of it, which we don't have to add to it, but that's there. But it knows, hey, I'm going to go look at B50:0 for whatever it is that you want me to sequence here. That looks good. So then what I want to do is I'm going to actually go into that B50:0 and determine what my sequence is. Now first though, if I only have B50:0, then I only have one step in my sequencer. That's not real helpful, right? Because we want to maybe turn on 3 or 4 outputs and kind of bounce around and show the power of this thing. So one of the things you may do in B50:0 is you may want to actually go to properties here and say, well, I don't want one element. I want to have, let's say, 8 elements. So now you'll see you get B50:0 through B50:7. So now I have 8 different elements of B50 I can use. So as an example, let's say B50:0, if I'm just using the first 4 bits there, those 0, 0, 0, 0. What if I wanted to turn on, the outer 2? Well, here's a 1, and here's a 1. So I can write to this data file and say, you know what? In B50:0, all the bits are zeros. However, in B50:1, bits 3 and 0 are going to be 1s. Oh, and by the way, in B50:2, bits 2 and 1 are going to be 1s. So I missed that one there. There we go. 2 and 1 are going to be 1s. And maybe I want to bounce out again. Here's a 1, and here's a 1. So you can kind of see how these are bouncing out. And there may be at some point where I say, you know what, I want to bounce out another one here and go into here, go into here, and go into here. And then maybe I do the middle three. And you can see this would be tricky if you're trying to do this with just, you know, bit logic, and maybe I'll do a 1 here and then I'll go back to a 0 at the end here. So in this case, if I'm at element 0 in the sequence, all the outputs are off. If I'm at element 1, outputs 0 and 3 are on. Output 2, elements 1 and 2 are on. Output 3, I get 0 and 3 on again. Output 4, I get 4, 2, and 0 on. Output 5, I get 3, 2, and 1 on. Output 6, I get element 2 on. And then output 7, I turn them all off again. Okay, that's kind of strange, but it looks like, wow, that might actually, you know, be an interesting sequence of how those elements go, right? But then the mask. Well, here's the deal. Remember how the mask works. Oop, I gotta go into B50 here. The way the mask works is these outputs are only going to turn on, or these elements are only going to be allowed to be used as long as they can come through the mask. So they have to be ANDed with a 1, right? Well, for the first 4 elements, I just need the first F, right? So I'm just going to do 0, 0, 0, 0, 0, F, and then a small case H is going to give me my hexadecimal. My destination then, though, is going to be O:2.0. The reason why it's a dot is because this is at the word address. So when I'm taking the B50 files and I want to move them into the output files, what I'm going to see is that I'm actually taking whatever's in. So if I'm at step 1 of the sequence, I'm going to move these bits into the output file. So in that case, element 3 and element 0 will turn on. Element 3 and element 0 will turn on. Okay, so you can kind of see what's going to happen with this thing as I move. And when I go to step 2, well, elements 1 and 2 will turn on. So elements 1 and 2 will turn on for that word, right? For that word address of O:2.0. All right, so that's where I'm going to put it. My control, if you remember what we did with our control, this is going to be our R6 address. So R6:0. Again, all that guy is, don't try to read too much into him, but all he really is he's kind of the traffic cop. You're saying, hey, here's some memory that the sequencer can use. Here's a location where you can, you know, some processing, some computing power where you can do some math or whatever you need to do, some instantaneous storage of bits, whatever it is. For length, I'm going to look at how many steps was I thinking in my binary file here. So my B50, you know, it looks like I got, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, something like that. I'll put a length of 8 in here for now. And position 0 is where I'm at right now. So now I'm going to do a real quick check on this, do a verify file. I can see I have no errors on this right now. Again, let's walk through it one more time. B50, this is my source file. This is where I'm going to get the data for what outputs I want to move, where I want to get my 1s and 0s from, determining what I'm going to turn on, what I'm going to turn off. That's what B50 is, but I've created that data file with all the 1s and 0s in it. The mask 0, 0, 0, F, and the little lowercase h means hexadecimal. So that means the first 4 bits, 1, 1, 1, 1, will be logically ANDed. So what that means is that I look at the B50 file, only elements 0, 1, 2, and 3 will be allowed to pass through. This 4 is not going to be allowed to pass through. I think it's kind of cool to see that, so I'm going to leave it that way. If I wanted that 4 to pass through, I'd have to change this to include that next element here, right? I could go 0, 0, 1 FH, and I would get that additional element. The destination, O:2.0, that's where these binary files are going to end up. Oh, let me get back in here real quick. There we go. So the binary files are going to go into output 2. So whatever step I'm at in my sequence here, that's going to get moved into this output 2 address, okay? Because that's my destination. The control, again, is my traffic cop. That's a little bit of memory that it can use to for instantaneous storing of bits and moving things around. The length is really how many operations am I expecting to perform here with the sequencer. And the position is which operation am I currently on. You know, it's almost like a preset and an accumulated value if you're talking about a timer, right? All right, so we're going to go ahead and download this. Download. It's asking me if I want to save it. Yep, I'll revise, save, and we're downloading it. Here we go. Once it's downloaded, I'm going to give it a second here, go back to run mode. I'll take it online, and we seem pretty good. This point, I'm going to pull up the binary file, B50, and I'm going to pull up the output file, O:2.0. I'm going to put these two guys side by side so you can actually see what's going on. Notice I don't have any output coils on my ladder at all. Even though I'm controlling 5 separate outputs, I only have one rung of code with a single switch and this little bit more advanced instruction called a sequencer, right? So now I'm going to go back into I lost those again, B50, and my output files. There they are. I'm going to flip my first switch. All right, now when I flip my first switch, what you'll see happened here is the sequencer went to position 1. When it went to position 1, it said, okay, what's in position 1? Well, my file is B50. I'm going to go look at B50:1. B50:1 says turn on or move. It doesn't really say turn on. It says move element 3 to a 1, element 2, element 1, both go to a 0, and element 0 goes to a 1. But you're going to put them in the destination of O:2.0. So now you'll see outputs 2/3 and 2/0 are on, which corresponds with this line of code right here, B50:0, right? 1001. 1001. So I'm taking what's in this location and moving it to that word. So now I have 2 of my outputs on. If you look at my PLC right now, I actually have 2 LEDs lit up. I'm going to sequence by flipping this switch again. Switch is on, switch is off. You'll notice my sequencer went to position 2 now, right? Now that I'm in position 2, I should be able to see what's happening in position 2. Here's position 2. I'm expecting 0, 1, 1, 0. Notice what happened in position 2, 0, 1, 1, 0. Pretty darn cool. If I go to position 3, my expectation is 1, 0, 0, 1. So when I go to position 3, flip the switch right now, I get 1, 0, 0, 1. Again, moving what's in B50:3 into O:2.0 is what I'm essentially doing. I'm moving the data that's in the binary file into the output word file. B50:4. You'll notice something strange happened here. Okay, I'm expecting a 1, 0, 1, 0, 1. I end up getting a 0, 0, 1, 0, 1. The reason why on this one is, remember the mask. What we did on this one was we said, well, I wanted to show you an example where this didn't work, right? And so what we did, let me go where we talked about a mask here, was we had 1, 0, 1, 0, 1, and then 0, 0, 0, F. All right, 1, 0, 1, 0, 1, and then 0, 0, 0, F. So this was what came out of our binary file. Our binary file was a 1, 0, 1, 0, 1. Our mask, though, however, was 0, 0, 0, F, hexadecimal. That 0, 0, 0, 0, F means I've got 4 zeros for the first one, 4 zeros for the next one, 4 zeros for the next one, and then I've got 1, 1, 1, 1 for the F, right? So when I mask this, yeah, the 1, 1, 1, 1 is this piece here. But that next area, 0, 0, 0, 0, when I logically AND these two together, I'm going to get a 0 here. I'm going to get a 0 here because I am, that's what I'm passing through, but I'm only going to get a 1 there and a 1 there. So that's exactly what happened as we looked at that. So if I wanted to change it, the easy way to change it would be to say, well, I'll just make it a 0, 0, FF. Hexadecimal. What that would do is that would change all of these to 1. So instead of these being zeros, these would go to 1s. And now whatever came through in that first byte would actually be transferred all the way through. But I thought it was good for you guys to see that, how that would work. But let's fix it. I really want that output to turn on. So I'm going to fix that. Can I fix it live? It looks like I can't fix it live, can I? 0, 0. Nope, can't fix it live. So what I'm going to have to do is go offline for just a second and make this a 0, 0, 0, 0, 0, FF hexadecimal. And now I have those first 8 bits as all 1. So I'll have a logical 1 with those first 8 bits. So I'll download again. And I won't be in the right position, so we'll have to go back to that position again. Well, maybe I will. We'll see where we fall here. So if that sequencer stays in the same position, am I going to have to sequence it through again? So I'm going to have to sequence it through again. But I'll bring up my binary files. There they are. I'll bring up my output files. There they are. And you can see it's pretty obvious right now. I'm in position 0. Position 0 is all zeros. So none of my... Oh, I actually do have an output on right now. That's some leftover stuff there. Let me go ahead and sequence through here. Okay, there we go. So now I'm in position 1. 1, 0, 0, 1. Okay. Position 2. Now you'll see 0, 1, 1, 0. There it is. Position 3. 1, 0, 0, 1. 1, 0, 0, 1. Now this is the one that we didn't get this bit before. The reason why we didn't get this bit before was because we were masking to a 0 in that 5th bit. So we need to see if we get that 1, 0, 1, 0, 1. There it is. 1, 0, 1, 0, 1. The reason why is because we have that extra F in here now. And I wouldn't have had to do an F. I could have done just that 1 bit if I wanted to. We'll go to the next location. 0, 1, 1, 1, 0. We'll go to the next location. 0, 0, 1, 0, 0. We'll go to the next location, which should be all zeros. The next location, all zeros. And we're at position 8 now. And then we're going to roll back over to position 1 again. And position 1 is right back to where we were here with the 1, 0, 0, 1. So, you know, what's the moral of the story here? The moral of the story is we've now got a much more advanced instruction that allows me to shift numbers around, shift bits around, control a lot of different things all at once without actually having to address every single one of these you know, I'm controlling all 8 of my outputs because I have 8 outputs on that relay output module, O:2/0 through 2/7. I'm controlling all 8 of those with this. You know, it's pretty easy to see. And oh, by the way, the neat thing about the sequencer, let's say I did want to have a step like down here where I want to turn on all of my outputs. I can hit 1, 1, 1, 1, 1, 1. So you can change these live. So you can see what's going to happen to this thing live. And so now, I pulled out the binary there. There we go. There's my outputs. So I'm on sequence 1 right now, which is right here. Let's flip through and get to the one step 7 here. So there's my 0, 1, 1, 0. That's the one I was just on. Here's my 1, 0, 0, 1, you know, looking over here. 1, 0, 1, 0, 1. 0, 1, 1, 1, 0. Now I've got the 0, 0, 1, 0, 0. Lines up perfectly. When I go to the step 7 of the sequencer, you're going to see a whole lot of 1s turning on. And one of the mistakes there, I didn't realize, sorry about that, is apparently one of my outputs is wired up to a buzzer. And all I had to do was flip through one more time to get all zeros going to the outputs. So that includes the lesson on sequencers. There will be a job sheet in this in the lab as well. But make sure, I hope you enjoyed the video, and I hope that helps you at least understand the basics of how the sequencer operations work.